All right, so we are continuing on with our investigation of Windows Azure in the real world, or the real cloud, or the real sky, however you want to think about it. And we're with Adrian Withy, who's a developer for Milliman. And you guys do some very interesting work that requires compute-intensive computation. So talk to me a little bit about what you guys do at Milliman.
Okay, well, at Milliman, we develop a suite of software called MG Alpha.
Okay.
MG Alpha is a life insurance pricing and projection system. It's traditionally been a desktop application, and we've developed that successfully for about 20 years.
Okay.
And about 2 years ago, we took the venture to port it to the cloud. Okay. And so we've spent the last 2 years developing both a new web-based management portal for management of actuarial models, cool, as well as a large-scale grid computing platform that we call MGL Compute for Azure.
Nice. Yeah. So the MGL Compute for Azure is very interesting, and certainly to our audience. Yeah. I'd love to know how that works. So okay, can we talk a little bit about that?
Yeah, sure. Well, MGL Compute for Azure is an HPC-style system. We have a long history of running HPC type systems. Our preferred is Microsoft HPC Server. And essentially what we did is we took that experience and we built an end-to-end HPC system within Windows Azure.
Okay. Yeah. Nice. So let's talk a little bit about, this is modeling software and projection software, so you have to be accurate, and you have to be pretty fast, and you have to use a lot of CPUs. Right? Or a lot of nodes, if you will, in Windows Azure parlance. So talk to me about going from the desktop from HPC to Windows Azure. I mean, what was that movement like?
Well, in essence, we have an embarrassing parallel problem, right? So we basically take a large set of input data, we distribute it on a lot of cores at the same time. There's very little collaboration between all of these different tasks. So we take a job, split it up into tasks. We run our core calculation engine. That's a native Win32 application, and we execute this on all of these tasks. We then combine the results, merge the results, perform some additional calculations, and then return the results to the user. And both with our desktop, so our desktop users can upload and submit a job straight from their laptop, and that will run on our grid platform. We also have a web-based UI that you can submit jobs in batch to, and then manage the results up in Azure as well.
Excellent. And so essentially, I mean, when you said task, you're actually using a task type from our parallel patterns library?
No, not really.
No, not really. Yeah. You just use that name. It's just classic. Take a bunch of data, break it up into pieces, compute all over it, join it back up, rock and roll.
Yeah, correct.
It's a classic pattern.
Yeah, and what makes it hard is that it has to be a very highly dependable system. So our customers rely on the results of these calculations for regulatory reporting. So there's financial implications for jobs failing or for results being incorrect. So there's, what makes the problem hard is both the dependability, where if we get a job, we have to finish it. We can't return a job and say, oh, it didn't work. And as well, the scale that we have to run on. We typically run at 10,000 cores or more. We have, we run at any time, we're running 15 different grid environments for different users, different customers, and different purposes. So,
awesome.
Yeah.
And so how's it working? How's it scaling?
Yeah, I mean, it's scaling great. I mean, we've been in development for about 2 years now. Really, hardcore, intensive development for 18 months. And yeah, it's running great. Yeah.
Great. Now, so you spoke about your development. Let's talk real briefly before we get back into the nuts and bolts of this. It turns out you have a pretty interesting agile development environment, and you have distributed development locations, right? So you have Seattle, you have London, you have other locations. Talk to me about your development process.
Okay, so we are an extremely agile team. We do both agile and extreme programming. We have 3 development teams. Each development team is about 4 to 6 people.
Cool.
And the way in which we manage the complexity of working in distributed teams, both distributed physically, as well as there's an 8-hour time difference between Seattle and London, is that we decouple the systems in the way in which you decouple a software system. So I mean, the interfaces between our systems are literally files and exes that we change as little as possible. So we have well-defined interfaces between our teams, and extreme programming doesn't allow you much time to pick up the phone and wait 8 hours for someone to come online. So we just make sure that we never have to.
Great. So let's talk a little bit about extreme programming. I mean, what is that?
Well, extreme programming.
I mean, I'm sure it's a terminology that means something, but
yeah. Well, I mean, extreme programming is really the practices, and there's some core principles behind it that you. I mean, we pair program on almost 100% of code.
Okay.
We do all test-driven development. We
Great.
have continuous integration, and so as an example, every time we check and code into our system, it'll run through various levels of tests, and we'll get feedback as soon as possible on the quality of the code that we've checked in. We, for example, when we check in, at one point, it will actually deploy a grid to Azure, ask the grid to spin up nodes, and then give it a job, compute the job, and check the results. Every single time we check in, it'll do this. Nice. So, if something breaks or if someone, we'll know right away. I think extreme programming is I think it's TDD and pair programming is the core practices.
Yeah, I mean, it's an interesting terminology. I mean, a lot of programming is extreme, like extreme programming, like, writing machine level code. So you mentioned exes and files. So you have this native component which basically houses all of your core IP and core algorithms for the compute intensive jobs it has to do. And then you feed it files. You give it a file location, it computes the data that's there and spits something back.
Yeah, I mean,
that's what I mean. Like what when you said exes and files?
Well, our core calculation engine is an example of where one team develops a component and it's used by another team, right? There's our core calculation engine is C and C++. A lot of it is dynamically compiled, on the desktop by the users, and we call that just using parameters. And it will know where its input is.
Great.
We don't have to worry about unmanaged calls and things like that.
No, we have to worry about interop between managed and native code because they don't even interact at all.
It's
great.
New process start.
Great. So let's talk a little bit about your architecture. So you're using Windows Azure Compute, you're using Windows Azure Blob Storage and Table Storage.
Yeah, so we use Compute and then we use Azure Storage.
Okay.
Azure Storage we do primarily blobs, queues, and tables.
Okay.
We try to do as much as we can between queues and blobs, keep it simple.
Okay. And then you have this portal that you've written as a web role in ASP.NET.
Yeah, ASP.NET MVC.
Okay.
Yeah, I mean, I guess I can give you a brief overview of our architecture.
That would be great.
Yeah. Okay, so I'll give you an overview of the MGL for Compute for Azure architecture. So let me start at a really high level. If this is the Windows Azure, and here we have MGL for Compute for Azure. At a really high level, we have desktop consumers that can submit jobs to us. We process the jobs and then we return the results. We also have a web UI that does the same. So that's it at a